These are kind of these cosmic metropolises, where you have hundreds of thousands of galaxies all bound together. And what we have found, the decades of comparing galaxies' properties with their environments, is that there's this divergent evolution that has occurred in our universe. So, as an example, so this is a plot. On the y-axis shows the fraction of star-forming galaxies. So 0 means there's no star-forming galaxies, 1 means they're all star-forming. And then on the x-axis, going left to right, you're going from less dense regions, so kind of these voids, to filaments, groups, and clusters to the most dense regions. And what we find is that galaxies that live in the dense regions are preferentially no longer forming stars. Their star formation has shut down. So this tells us that there's some physics that's going on that's suppressing star formation. Similarly, if we look at the morphology of a galaxy, what's its shape? So this plot is similar to the one on the left. The y-axis here shows the galaxy morphology fraction, split between these spiral galaxies, these lenticular galaxies. They have this flattened disk, but they don't have like spiral arms. And then you have elliptical galaxies. These are kind of like these egg-shaped galaxies. And what we see is that in low-dense environments, we see tons of spiral galaxies. But as you go to denser and denser environments, to these groups and clusters, you find very few spiral galaxies, but more elliptical galaxies. Again, this tells us environment plays an important role in shaping galaxy evolution, specifically in these galaxy clusters. Now, my research has mostly focused on clusters. Again, these are the most extreme environments, and this is where we see these trends these differences in galaxy properties are most pronounced. And I just want to show you this image. This was released early last year when the Vera Rubin Observatory showed its first science images. And this is the Virgo cluster. This is the closest cluster to our planet. And you can see kind of the cases where you see these elliptical galaxies. In this case, these are giant elliptical galaxies. These are some of the most massive galaxies that have ever been formed, and you find them in galaxy clusters. Another example, this is an older image from Hubble. This is showing another cluster that's fairly close. This is the Coma cluster. This is a very massive cluster. And again, you see these giant elliptical galaxies. And what I want to convey to you tonight is that galaxy clusters hold clues to the universe's biggest mysteries. And I'm going to go through a few examples here. So galaxy clusters are extremely massive. And what they do is they warp space-time itself. So light from background galaxies that passes through a cluster can actually get bent. And you can get duplicates of these galaxies, these called lens galaxies. And by studying galaxy clusters and using this fact that they warp space and time, we can learn about our cosmology. So our universe is expanding, and we want to measure that rate, and we can use clusters to do that. And this was done very recently. There's a team out at Arizona or University of Arizona that used imaging from the James Webb Space Telescope to find this galaxy cluster. And you see these arcs here. These are galaxies that are in the background that have their light kind of stretched out as it passes through where the galaxy cluster lives. And what they found by studying this galaxy cluster is something very fascinating. So here, this is this box I'm showing. We zoom in a little bit, you'll see these 3 dots. So I'll give you a second just to guess what these are before I show you. So these are kind of point images, but they're very bright. And again, these red curves are kind of the galaxies that's been stretched out by the gravitational lens that the galaxy cluster creates. All right, so if you thought about it, so the answer to this is a star that has gone boom. This is a supernova. And it's known as supernova hope. So it's kind of a play on words. So H0, we call this H naught. This is a parameter that quantifies the expansion rate of our universe. And because this star went kaboom, it passed through this cluster, and all the light took different times to reach our telescopes. And by measuring the time delay, we're able to infer the expansion rate of the universe. But before I kind of go into that, I want to show you this visualization. So this is what we think the star that went kaboom looked like, the supernova. So you have this stellar remnant in white. It's kind of siphoning off gas from a more massive companion to a point where it reaches a critical density and just explodes. All right, so this is what we think happens, and this is what was captured in this JWST image. So by studying this system over a course of time, they found that certain points arrived earlier than others. So here at the very top, you have image A. This was the light that first arrived to the telescopes. And then you have image C arrived about 10 weeks later, and you have image B that was about 4 months later. So by doing some modeling of the system, folks were able to infer the expansion rate of the universe using galaxy clusters. So learning about how the universe is expanding by studying these extremely dense systems. And this is another image that I wanted to show where you can see this cluster, this lens region back in 2023 versus 2025. You can see where, before there were no lights and then the light show began. And after that, it faded away. So galaxy clusters, again, unlock mysteries to the universe, in this case, the expansion rate. Now, galaxy clusters are also extremely hot. So you can't see this in the visible. So the optical is the light that we see with our own eyes. But if you were able to point an X-ray telescope at a galaxy cluster, what you would see is that the cluster glows. And it glows in the X-ray, and it's showing the presence of a superheated plasma that we call the intracluster medium. And just a few cool cluster facts that I want to share about the intracluster medium. So if you compare to the surface temperature of the sun, it's about 1,000 to 10,000 times hotter. Additionally, if you add up all the mass from the stars and the gas that's in the intercluster medium, you'll see that it's about a factor of 4 times larger, or more abundant than the stars itself. But by doing that, when we study the gas in the stars in the cluster, it's still not enough to keep the cluster bound. There's about 85% of mass in these clusters that we cannot see. We call this dark matter. Invisible matter, we know it's there by its gravitational impact, keeping these clusters together, but we cannot see it. But by studying galaxy clusters, we can get an idea of what this stuff might be. And I'll show you with an example. So this is the bullet cluster. This is one of the most famous clusters in the literature. And what's interesting about it is that these clusters in the past collided. And by looking at where the gas is distributed, using our X-ray observations, and using where the mass is distributed by looking at these gravitational lenses, we see something fascinating. So these are our two clusters. You have the big one on the left, the smaller one on the right. That's when it kind of passed through the big one on the left. And now I'm color coding this by the gas in pink and where the most of the mass is at in blue. So what you can see with the pink gas, you can see that it creates this bow essentially, that where the gases plow through it and they're interacting kind of in the same way that as a boat goes through the water, it creates this kind of bow-shaped shock wave. So the gas is interacting with each other. But if you look at the blue colors, essentially they pass through each other without leaving many signatures of interaction. So what this tells us is that whatever dark matter is, it's weakly interacting. And this helps us kind of build our theory of what this mysterious substance is. Again, helping us solve the mysteries of the universe. And kind of going back to my work, which is focused on understanding how the environment impacts the properties of galaxies in terms of their star formation activity or their morphology, this hot gas within clusters impacts the way galaxies can hold on to their gas. So this is a visualization I'm going to show you of a galaxy here, and it's moving through a cluster. As it moves through, it has its gas kind of ripped from the outside in. It's this pressure that's been exerted on the galaxy due to the presence of this hot gas. So this is just a visualization, but this is an image of an actual galaxy passing through the normal cluster, shown here. And we call this process ram pressure stripping, and these galaxies are known as jellyfish galaxies due to their tendrils that are being kind of pulled apart with the gas being pulled apart from the galaxy. So I want you to take away that galaxy clusters are very important for helping us understand a lot of mysteries in the universe, from the expansion rate to maybe what dark matter could be, what's its properties, and even how environment impacts how galaxies evolve. But there's still so many open questions in our field. The first one is, how did these cosmic behemoths form and grow in the first place? And on top of that, how did these galaxies, these giant ellipticals grow, right? Today, these giant ellipticals that I showed you at the very beginning, they're kind of like dinosaur fossils. We see the final product of some evolution, but we don't really know what they looked like. How did they grow? Was it through multiple mergers of smaller galaxies building up these massive galaxies throughout time? Or was it just due to these extreme bursts of star formation where galaxies just grew by consuming gas from their environment? So these are questions that we want to know by studying the earliest stages of galaxy cluster assembly. We want to understand the role of environment in galaxy evolution. So this is a question that I'm currently pursuing. When does environment begin to suppress star formation in galaxies, in these proto-cluster galaxies, galaxies that live in clusters that haven't quite formed yet? We also want to understand just the large-scale structure of our universe. How do the largest gravitationally bound structures in the universe form and evolve? And also, we understand the properties of this hot gas. How did it form? How did the intercluster medium form? When did it form? And other mechanisms that related to that. So to do this, there's one way we can just look at an image of a cluster today. This is how we study how things evolve observationally. We can find, okay, this is a cluster in the nearby universe, and we can find progressively for the clusters that are further and further away from Earth. So we can't look at an individual galaxy and do this longitudinal study. We just don't have enough time, but we can look at different clusters and see how they look at different times in the age of the universe. And what we do from just kind of this analysis is that we see that most of the galaxies in clusters up to the past 7 billion years, they all have very low levels of star formation and they exhibit these elliptical morphologies, kind of like what I talked about before. But as you go further back, let's say 9 billion light years away, and the record holder right now for the most distant cluster that we found is about 11 billion years ago. Most of these galaxies tend to be more star forming. So this tells us that while galaxy clusters today are kind of like these cosmic graveyards with galaxies that have long shut down star formation, in the past there were these booming cosmic metropolises where galaxies were taking in gas and forming new stars more readily. To show you this with a diagram, so here to the left, you just have a visualization of the large scale structure, the cosmic web of the universe today, and then you can just point out a node where a galaxy cluster might live. So kind of the picture view that I want you to have of the clusters today, they're fairly collapsed. Most of the mass is concentrated in the center, and you have all these galaxies that are no longer forming stars. You can, as shown here in red. But as we go back in time, we find that clusters are actually more extended. There's more star formation going on in there. As we go earlier and earlier to young clusters, again, more extended, more star formation, till we go to a stage called the galaxy protocluster stage. These things are they haven't collapsed yet, but what we think from our models is, and from our observations, that these protoclusters are characterized by having a dense core of galaxies that are forming stars at a very, very high rate, surrounded by galaxies that will eventually collapse and become members of the cluster by the present day. And this is the stage of galaxy cluster assembly that is poorly understood, that I'm currently studying, members of collaborations that I'm in are studying, but it's challenging to study this stage for a number of reasons. So as you can see with this diagram, the first one is that these structures are enormous, right? Let's give a concrete example. So take the full moon. So protoclusters actually cover roughly a third of the full moon in the full moon's width on the sky. So on top of that, they're rare. So in order to find these, you need wide area surveys, scanning the sky and measuring distances to galaxies. On top of that, the techniques that we've refined to find galaxy clusters become ineffective in the distant universe when we look for these protoclusters. So clusters today, these mature clusters, can be identified in different regions of the electromagnetic spectrum. So here I'm showing you an image of the Coma cluster in optical. You can see all of these yellowish elliptical galaxies. We have a method known as the red sequence method to find galaxies in the optical. In the X-ray, we can see presence of this hot plasma, this intercluster medium that I talked about. So you can see in the X-rays, you can also see signs in the sub-millimeters. So these are kind of longer wavelengths than what we can see with our eyes. So this is how we can find clusters today, just looking at the overdensities of galaxies that look elliptical, seeing if they have some signatures in the X-ray or sub-millimeter. However, when we try to apply these for protoclusters, they just don't work. They lack these distinctive signposts. So galaxy protoclusters lack this distinctive population of elliptical galaxies, and what we call the proto-intracluster medium is much cooler and less dense, making these X-ray and submillimeter signals extremely challenging to detect. So how do we actually find these progenitors, these ancestors to the clusters we find today, so we can answer these questions about how these most massive galaxies formed, when did environments start to suppress star formation? Well, to do that, one way is to identify kind of the densest galactic environments in the early universe by obtaining very accurate distance measurements over a wide area of the sky. Again, these are things that are enormous, and we need correct distance measurements to identify these overdensities in the early universe. Now, this is, I want to show you this example. So it's easier to do in person when I can see you all, but I'll just give you time. So can you spot the imposter? I want to show you what's known as projection effects. This is kind of like the bane of my research, where you have galaxies that look like they are correlated with each other spatially, but one's actually in the foreground in front of the others, or one's in the background. So this is a famous galaxy group. You may be familiar with this. It's known as Stephan's quintet, and there's 5 galaxies here. So I labeled them A, B, C, D, and E, and I would just take a moment to guess which one is the imposter, which one is not associated spatially with the others. So I'll just give you a second to think about that, and I'll show the answer. I'll take a sip of water. Okay. All right, so if you have your answer, just hold that in your head. So turns out that this galaxy here, option A, NGC 7320, is the imposter. It's not spatially correlated with the others. And the way that we can determine that is actually measuring their distances to all these galaxies. And we find that this galaxy is actually a foreground galaxy. So these other galaxies are further away than this galaxy is. And this just goes to show why it's important to get accurate distance measurements in order to make sure that what we're claiming is an overdensity, or galaxies that are kind of packed together, is truly galaxies that are packed together and not just some projection effect. So this is the image from the James Webb Space Telescope. It's actually a little bit kind of easier maybe to see if you look at Hubble image, just because it's just more a blue spiral galaxy, where these other ones are kind of interacting. But it still goes to show that measuring distances is very important, and making sure that you have accurate distances. But the issue with that, the issue with getting accurate distances over a large swath of sky, is that it's observationally expensive, right? A lot of the times when you put in a proposal to observe something, you don't want to just go on like a fishing expedition. They want to say, okay, I know this object is there. I just want to get this extra data to make sure that I can make this new claim. So in this case, you want a telescope that can survey the sky, and it's kind of not looking for anything in particular. So one solution that was adopted early on was to limit these searches to galaxy populations that are unique to the distant universe. So if you know these galaxies are going to be only found in the early universe, if you can find those overdensities, then maybe what you're looking at is a galaxy protocluster. So this is an example of how this was done earlier on, late 90s. So there's these galaxies known as Lyman break galaxies. And they are essentially just normal star-forming galaxies in the early universe. But what's interesting about them is that if you go further back in time, the intergalactic medium, the space between galaxies, was composed of more neutral gas, neutral hydrogen. And the light emitted by these distant Lyman break galaxies would get absorbed on its way towards the Earth. As you can kind of see in this image, you have this distant galaxy, and in between Earth and the source, there's a bunch of gas. And if you kind of look at their spectrum, so what this shows on the top is the relative flux. You can think about the amount of light that's passing through as a function of the wavelength you're looking at. So on the left, you have bluer light, and on the right, you have redder light. And these galaxies are characterized by having this kind of break here towards the bluer wavelengths. So we call this the Lyman limit. And while you need to get something known as spectroscopy to measure this, which is far more expensive than getting something as imaging, you can actually identify these galaxies using imaging alone. And by doing that, you can just basically take an image of a galaxy in a narrow wavelength range at redder colors and progressively bluer colors. So in this case, you have it in the I band and you have in the V band, you see it in the B band. But once you go past where this break is occurring, you don't see anything because the flux has dropped down so much here. So this is one way that folks were kind of cheaply able to identify these distant galaxies. And one of the earliest known galaxy protoclusters was found in the late 90s by Chuck Seidel at Caltech. And what they found, they took a sample of these galaxies that exhibit this dropout where you would see it in images that are fairly red, but it would drop out in bluer images. And they went and followed up and got distance measurements to measure its spectra. So this plot here is from their paper, shows the number of galaxies as a function of redshift. You can think about it as distance from us. So things on the left are closer, things that are right are further. And you can see this huge pileup of galaxies. And this is what we call the protocluster. So this is showing the position. So all of these dots represent the galaxies in the structure, the ones that are circled. And then on the right, you have the 3D representation of this protocluster. So this is SSA 22. This is the earliest known galaxy protocluster. And this study is important in the field because it showed us that, oh, we can actually find these things. So throughout time since then, folks have found other tracers of galaxies in the early universe. So you have these normal star-forming galaxies, these Lyman break galaxies. Other folks have used galaxies that are both dusty, they have very high rates of star formation. Again, I mentioned earlier the cores of protoclusters are thought to be regions where a lot of star formation is happening. So use these galaxies as tracers. They've used something known as ultramassive galaxies, something like 100 galaxies that have 100 billion solar masses in mass in the early universe. Folks have also used something known as high redshift radio galaxies. So these are galaxies that have supermassive black holes in their center of galaxies that are sucking in gas and shooting them out along kind of these jets. And they think these are also indicators of being in a dense region where there's a lot of gas. So the issue that we have now is that we have the zoo. We have all these different tracers of overdensity of galaxies in the early universe, making it extremely difficult to understand kind of what is actually going on with these systems and interpret the data. And just to show you kind of images of these different systems. So here on the top left is that SSA 22 protocluster that I talked about earlier. That's one of the earliest found. But there's also these other ones that are using different tracers. They're also using different fields of views. So these things are enormous and they're not always kind of probing the full structure. And again, this just makes it very difficult to understand what is going on in these structures and get some uniform and a uniform sample to understand how galaxy properties are evolving in these early structures. So for this reason, if we look at the number of confirmed protocluster samples as a function of time, so this is what this plot is showing on the y-axis, the number of discoveries from the late 90s to today. So we've only found around 60 to 70. So the sample sizes are fairly small. We found thousands of galaxy clusters, but only less than 100 galaxy protoclusters. And again, they're all heterogeneously sampled. So right now, it's really hard to do these population level analyses to understand some of the main questions that I shared earlier. But we are in a time where we have these new facilities coming online that are going to be able to answer these questions. So this is where I'm going to transition to the next part of our talk. So this is the frontier of protocluster research. So it's not all doom and gloom. We're not just stuck with this galaxy protocluster zoo and small samples. There's hope on the horizon. So I'm going to talk about some recent advancement and some future outlooks. So the most glaring change that has happened has been the launch of the James Webb Space Telescope. So it has allowed us to detect galaxies in very early universe. We keep finding these record-breaking galaxies earlier in age of the universe. And this is just due to the James Webb sensitivity to very red light, right? As the universe expands, these galaxies emitted light that was initially blue, but it just stretches it out. So James Webb allows us to appear early in time. And one discovery that I want to show out is um, in the background of this Pandora cluster. So kind of these elliptical galaxies here are part of the Pandora cluster, but in the very background, recently, folks have measured or found these 7 galaxies that are taking are forming when the universe is about 650 million years after the Big Bang. So this is kind of the earliest galaxy protocluster that we think we have found so far, and this has been thanks to the James Webb Space Telescope. But the issue, though, is that the James Webb Space Telescope field of view is fairly small, so it's hard to probe these large areas. So if that was a true protocluster, it was most likely just looking at the densest region or the core region. And this plot here just shows kind of the state of things right now. So in yellow, this yellow region shows all the clusters that we found, and the top of this axis shows the age of the universe. So we found thousands of clusters, but again, less than 100 galaxy protoclusters. But James Webb is changing that, specifically looking at things that are the most distant likely protoclusters. Also, James Webb has found this amazing structure known as the cosmic vine. So it's a chain of 20 galaxies spanning 13 million light years. This was seen when the universe was about 1.5 billion years old. So in this image, they found galaxies that appear to be merging. So in this study, they are claiming this prop is likely signs of these galaxies forming to create these giant ellipticals that we see in the present day. So this, again, we're seeing science answering the questions of how did the most massive galaxies form? In this case, it looks like these 2 massive galaxies are forming together to make an even more massive galaxy that might be a giant elliptical today. And this is all thanks to the James Webb Space Telescope. But James Webb's not doing everything. So there's also the Atacama Large Millimeter and Submillimeter Array down in Chile. And this is allowing us to look at the origins of this intercluster medium, this hot plasma. And this is the spiderweb protocluster. This is probably the most well-studied protocluster in the literature. It's been looked at across the electromagnetic spectrum with telescopes both in space and on the ground. And what ALMA was able to do is find signs of this proto-intercluster medium in this protocluster. So this is ALMA, and I want to show you a short video kind of showing what they were able to find. So all of these red streaks here are representative of particles of light from the early universe. And then this plasma cloud, like this early protocluster, intercluster medium is shown here. And they have these free electrons. And you have these photons in the background interacting with these electrons. They have low energies, but after interacting, they have higher energies. And this leaves a signature that was able to be detected with ALMA. So this blue kind of blob is showing the signature that was found within the spiderweb protocluster. So this is kind of signs of the intercluster medium. It's showing that even like 10 billion years ago, this intercluster medium was starting to form. And folks are trying to understand what this hot gas, what impact is it having on the galaxies that live in this protocluster. So that was on the observational side, but at the top of this, I mentioned that I'm both observational and computational astrophysicist, and I've been using these next generation cosmological simulations to try to bridge observations and theory to better understand and develop surveys to search for galaxy protoclusters. So what you're seeing here is a cluster forming within a cosmological simulation. So this simulation was run on a supercomputer. It includes gravitational physics, physics for forming stars, includes gas, magnetic fields, pretty much anything you can think of is all included in the physical prescriptions in this model. And we can actually see how galaxy clusters, at least in theory, should form from the early universe to today. So I've used this simulation to try to understand how our inability to fully probe the galaxy populations and distant protoclusters impacts our ability to interpret trends that we measure. So with this data, what I've done in a recent paper was starting off at a cluster today. So this plot is just showing the X and Y position of all these galaxies shown in white that are part of a cluster. And then I can evolve, basically look back in time and see where these galaxies were 8 billion or 12 billion years ago. So this is during the protocluster stage, the stage prior to collapse. And what I've done in this paper is that I've selected a population of galaxies that are complete, meaning that I know that these galaxies are fully representative of the system, down to a stellar mass of 10 to the 8.5. So I have a baseline population of like, oh, these are all the galaxies I know are there. And in this plot, I just want you to focus on this red cross here. So this is the densest region of the protocluster, what we would call the core, and we're looking at how it evolves with time. So the cool thing about simulations and why I like to use them to try to understand our observations is that now I could degrade our sample. So I have a baseline population that I know is complete, but then I can make it mass limited. So when we go and observe these samples, we're not going to find the faint things, the low mass things. We're more likely to find the brighter things, more massive things. And my study was asking, okay, if we're missing the faint things, how does that impact our ability to reconstruct the density field of the protocluster? And in this one example, it kind of does a good job at finding where the densest region is at some cases. So these different panels to show different time steps. So blue is kind of later in the universe, red is earlier. But I did this in a more statistical sample. So this is just one galaxy, but I took over 352 galaxy clusters and I did the same measurement. So this plot on the left is just showing the threshold that is less restrictive, meaning that in this case, if you look at where the highest density peaks overlap compared to where we expect them to be, we recover them in about 65% of the cases. So we're truly probing the density field and we're finding the densest region. And the reason that we care about this is that we want to quantify galaxy properties with their local galaxy density. But like in this middle panel, if we're only sensitive to galaxies that have stellar masses greater than 10 to the 10 solar masses, we're missing almost half the true densest regions. And it gets worse as you are only limited to the most massive galaxies. So kind of this paper that I recently had accepted for publication just shows that it gives a way to quantify, if we're only looking at the big and bright guys, how much we're missing or what impact that could have on our data that we interpret. And another cool thing that I was able to answer with this project is how exactly do kind of what we call selection functions. So any survey that you're doing with galaxies, it's going to have some inherent selection functions. You may not be able to look at galaxies that are above some brightness, for example. How does that impact our ability to impact the trends that we observe in protoclusters? So I'm going to show you two trends here. The first one is that in the densest regions of protoclusters, galaxies tend to be more vigorously forming stars. So this is shown here. So these are all galaxies that are in a protocluster, whereas the red ones are in the densest region of the protocluster. So if you look at a fixed stellar mass, which is on the x-axis, the ones that are in the densest region tend to have higher rates of star formation, which is the y-axis, compared to these gold ones. But my question was, how exactly does this depend on the completeness limits of your survey? And another trend that has been observed in literature is that the most massive galaxies that we see in protoclusters tend to be in the densest regions. So here on the right, we have this scale going from blue to red. So blue are kind of the lower mass galaxies, white are kind of intermediate, whereas red is the massive galaxies. And kind of what's shown here is that in the densest region of this protocluster, that's where the most massive galaxies are found. But with these simulations, we are able to kind of test this and see how exactly our baseline sample will compare to a sample that is more compared to reality of what people are actually observing. So how do we do this? So one way is just take a protocluster at some time in the universe, and we find the densest region, and we just look at the average, for example, stellar mass within this dense region and compare it to the average stellar mass or star formation activity outside of this region. So kind of shown in yellow and blue respectively. And then you can take this ratio, and if this ratio is greater than 1, we know that we're seeing an enhancement in the densest region. If it's less than one, we see a suppression or a depression. So this is something that I looked into. So this is just using a sample that's complete. We know that all the galaxies are representative in our sample. And what we found is that at the time in the universe where we expect to see protoclusters, we are still seeing this enhancement within our simulations in terms of the star formation activity. So this is shown in this plot here. So this gray line is just showing kind of where a value of 1 would lie. So everything is above that in terms of like the mean and median value of our samples. And the same thing is seen for the most massive galaxies. So they're all above unity. So we're reproducing kind of these trends that are seen observationally, even though that we have a complete sample. So despite them being incomplete, despite them sometimes missing the densest regions, the qualitative trends are still the same. There's this enhancement in the densest regions of galaxy protoclusters. So all this work is helping us kind of interpret what we're observing through the eyes of simulations. And all of this kind of goes to some additional observational work that I'm a part of. So I'm a member of a collaboration known as the Charting Cluster Construction with VUDS and ORELTS, or the C3VO survey. And this survey is kind of helping us address this protocluster zoo problem by not selecting just individual galaxies, highly star-forming galaxies or massive galaxies, but we're taking all the galaxies we can find and we're getting spectra, we're getting distance measurements of these galaxies using the Keck telescope and the Gemini telescopes on Mauna Kea. So this is an example of one of the protoclusters that has been found with a C3VO survey, and we've identified kind of the densest regions. And this is what it looks like in 3 dimensions. So my simulation work is kind of helping inform and interpret some of the observational work. And I just want to share with you some of the cool things that we found from this observational study. So one thing that has been found is that in the earliest dense regions of these protoclusters, we're seeing more signs of something known as AGN activity. So AGN stands for active galactic nuclei. It's kind of shown in this animation. So these are supermassive black holes that are kind of accreting matter and ejecting them along these jets. So we find that in the densest regions of our protocluster, we're more likely to find these AGN. So this is really cool, and the simulations again can help us interpret kind of what is causing this, and it's likely just due to more gas being present in these dense regions. Another cool trend that we have found is that if you look at the fraction of star formation in protoclusters as a function of time, which is shown by this plot, we have expectations from simulations shown here by these colored lines, and then we're able to actually make measurements to compare to these predictions. And we're finding that in the early universe, these protoclusters are contributing significantly to what's known as the cosmic star formation rate density, how much star formation is going on at the time in the universe. So protoclusters, again, are these bustling cosmic cities with a lot of star formation going on. And we're actually showing this observationally, and it agrees with our predictions from our simulations. And this is interesting because there's a time in the universe known as the epoch of reionization, and it's thought that these protoclusters are playing a major role in this epoch. So what is the epoch of reionization? So this plot here shows the evolution of our universe, going from the Big Bang to today, 3.8 billion years later. So in the early universe, it's very hot, it invented cooling, and you had atomic nuclei, protons, and electrons coming together during the epoch of recombination. And then you have this dark age where not much was going on until the first stars started to turn on. So during the dark age, the universe was mostly composed of neutral hydrogen, so hydrogen with its electron bound together. But once these stars and galaxies started to form, they started releasing high energy radiation that started to strip away electrons from the protons in these hydrogen atoms until you get to the universe today, which is fully ionized. So this is this yellow box is kind of showing this epoch of reionization. And we think by studying protoclusters and getting these uniformly selected samples, we'll be able to really understand how they contributed to this kind of crucial stage in the universe's history. And this is kind of showing a visualization that I really like. So red is kind of the neutral hydrogen, and this grayish are showing kind of the galaxies. And, as they turn on, they release photons, essentially. They're getting rid of this neutral hydrogen and turn it into the ionized hydrogen. So again, protoclusters, by studying these early stages of galaxy cluster assembly, we're going to be able to study more and learn more about this epoch. Okay, so I talked about James Webb, I talked about ALMA. These are two facilities that are currently online, but there's still more along the horizon. So I'm going to come back to this plot. This shows the cumulative number of discoveries of protoclusters as a function of time. So as of today, we're still less than 100 that have been confirmed. We have secured distance measurements over some large enough area to say, okay, this is likely a cluster progenitor. But at the end of this year, the Nancy Grace Roman Space Telescope will launch, and it's going to be game changing. Predictions show that we'll find over 1,000 galaxy protoclusters with this. And why is that? So if you compare the field of view of Hubble, which is shown here, to the Nancy Grace Roman Space Telescope, it's about 100 times larger. Again, we need these large, wide area surveys to find protoclusters. On top of that, it has a slewing speed, how much it can turn and move as a function of time. That's about 10 times faster than Hubble. So overall, it's going to have 1,000 times surveying speed, allowing us to probe these huge volumes of the universe and get these distance measurements to find these galaxy protoclusters and select them in a very uniform way, not dependent on a specific galaxy type. Again, helping address this protocluster zoo problem. So this is research that I'm currently preparing for. There's open proposals for Roman that I'm working on right now with my team, and I'm very excited. I'm so excited for this telescope to launch and start to analyze this data from. But on top of that, it's not just Roman that's out there. I talked about the Rubin LSST that took this image of the Virgo cluster. So this is amazing because it has this ultra deep imaging. It's going to do this 10-year survey, taking images of the sky. And we're going to use this data in conjunction with the Nancy Grace Roman's data, in conjunction with the James Webb data. And there's also a space wide field telescope launched by the Europeans, Euclid, that we also will take advantage of to really have a full understanding of the earliest stages of galaxy cluster assembly. To answer some of these questions that I talked about before, how do the most massive galaxies form? When does environment start to impact galaxy evolution? When does the intercluster medium start to form? And so on and so forth. Okay, so I've talked about kind of these very massive things on these long time scales, 13 billion years. So I want to leave you with a quote that kind of always keeps me grounded. So it goes, she had studied the universe all her life, but had overlooked its clear message. For creatures such as we, the vastness is bearable only through love. So with that, I want to thank you. Thank you for having me. Thank you for letting me share some of the work that we're doing here at UC San Diego and kind of giving you an idea of what's to come with these future observatories. And I want to just end with some acknowledgement of my collaborators and my funding sources. So thank you all so much for having me here. It's been a pleasure. And I'm open for a question and answer session if that's what follows this.
Thank you so much. Yeah, I have questions too, but I'm going to defer to the audience. People I'm sure have a lot of questions. Yes, please.
The protoclusters tightly gravitationally bound or loosely bound?
Did you hear that, Dr. Baxter?
So was the question that our protoclusters
are-
gravitationally bound or loosely bound?
Yeah, are they loosely bound or what was
Great,
that?
great question. Yeah, so the densest regions, the core regions of protoclusters, these are gravitationally bound systems. But all the galaxies on the outskirts that we're seeing, especially in these simulations, observations, have yet to become kind of gravitationally bound. So with time, they're going to collapse, but at times of observation, they're not bound yet. And that kind of goes on to another issue or another challenge that we have in kind of this field is like understanding which of these galaxies will truly be part of the cluster later on in time, right? So, that goes into modeling, making sure that, okay, these distances are close enough. They And they will likely, like you can do some statistical analysis to see like which of these galaxies would more likely be part of the structure today if this thing were to evolve over 10 billion years or so.
Yeah, go ahead.
Can you hear me?
Yes, I can hear you.
Great. So thanks, a very interesting talk. In terms of the environment, you focused on, as I understand it, mostly the density of the galaxies, whether they're sparse or dense.
Right.
And as you're looking out further back in time, I'm wondering if the change in the composition of the elements also matters or not. So in the very early universe, it was mostly hydrogen and helium, and over time, the stars start forming more heavier elements. So, as we get to the more recent stars, we have a lot more, say, carbon and iron and so on. And is that change in the composition also a part of the environmental change that confounds how you compare recent versus old galaxies, or does that not really matter that much?
That's a wonderful question. So the question, if I understand correctly, is that there's this stellar evolution. Early in time, we had mostly hydrogen, helium, but we get these heavier elements in the age of the universe. So what this area actually comes up in studying kind of galaxy environments. There's something known as the metallicity density relation. So in denser regions, we sometimes see that there's more metals being formed there. These populations tend to be older compared to kind of less dense regions. Um, and one thing that we want to understand is that how does this trend emerge in clusters? You have these competing factors that you have to consider, though. So you have gas coming from the intergalactic medium. We call this pristine gas. It's mostly hydrogen. It's not kind of diluted with these heavier metals. But within these galaxies, especially within these clusters, these kind of like closed systems, so you have a bunch of metals. Um, so there's this competing factor of like some folks have found that there's kind of an elevation of heavier elements in galaxy clusters and protoclusters. Other folks are finding no, that's not the case. But I think the answer to this is kind of dissecting how much gas has recently entered this cluster versus because I think that's another case that could, again, if you get a bunch of pristine gas, a bunch of hydrogen, the signal that you measure for the metals will be just it'll be changed essentially. So that's another open question that folks are studying. I have a project that in mind for someone to look at that in simulations, but yeah, great question.
Thank you.
Um,
Hi, Antonio. This is
yeah,
Vikas.
hey,
How are
Vikas.
you?
Yeah, go ahead, because
Thanks, Antonio. Thank you, Dr. Baxter. That was absolutely fascinating. Probably could listen to that 2 or 3 times. Just a quick one. If you could please put up the previous slide, the one that had your references and the collaborate. Oh, there you go. Perfect. Yeah, that went by really fast. So
Sorry. Yeah.
so perfect. Thank you. And if you wanted to pull out some of your papers, what would be the easiest way to do that? Just go to the GitHub site or?
Yeah, you can go to my GitHub. That's my personal website, and it has kind of like an overview of my research and my papers there.
Okay, yeah. Thank you so much.
No worries.
Yeah.
so, yeah, go another member for the audience. Yes.
When you're doing your simulations, they talked about the effects of dark matter. What about dark energy? Does that affect your simulation?
Mhm.
So usually most of the simulations today kind of have just so dark energy is just this repulsive force essentially that could speed up the expansion rate of the universe. Usually we just have a kind of singular model where we have dark energy applying. Not many folks that I know of are playing around with dark energy just so because we don't know very much about it. We just know that it seemed to be kind of slowing down the expansion. Um, so the answer to that is no. But there are folks that are looking at different flavors of dark matter. So you can have folks that are looking for dark matter that are more interacting, dark matter that can move kind of near the speed of light, dark matter that is kind of relatively slow. So there's people that are doing different models to see kind of how your different dark matter prescriptions change. And Yeah, there's some, and what it really changes is the abundance of galaxies, essentially. So our current paradigm is known as lambda dark matter. So you have some expansion due to dark energy, and then we think this dark matter is kind of weakly interacting, and it leads to kind of more structure than you would get if you had kind of more interacting systems.
I have a question. I've been, many of us are listening to many presentations about the Vera Rubin telescope, and that's essentially coming online. I, is your team able to access that data? Because I'm hoping that that would increase the number of protocols clusters that you could observe.
Right. So the question is like, will we be able to use Vera Rubin? So Vera Rubin is funded by the National Science Foundation and the Department of Energy. And if you are in the United States working on research, you can access this data. It's all publicly available. The first data release hasn't actually come out yet. We have it. We actually had a talk here at UC San Diego from Eric Bellum. He's a professor at UC University of Washington. And he was telling us about kind of the dates that we could expect data to be available. And I think the earliest was late 2027, 2028 for the first data release. But
Oh,
again, this
wow.
is a 10-year program. So absolutely, there's going to be some overlap between Roman and the Rubin LSST survey that we will take advantage of. This is going to mostly do imaging, but we will get some crude estimates of the distances, something known as kind of photometric redshift. So you don't actually have its spectrum, but you have enough images and different bands that you can kind of reconstruct, get an idea of what the spectrum might look like. And that gives you an idea what the distance is. So we'll absolutely, and this is going to help us kind of get these lower mass galaxies, these fainter galaxies that are going to be missed by the the Roman Observatory.
Yeah. Yeah, it's the images that are coming out are stunning.
They're amazing. They're beautiful. And
Yeah.
so I love it.
Yeah. Um,
Yeah, recently they had some bad weather. So they had the during the winter in the southern hemisphere, they just couldn't do much observing. So
uh,
uh, they take what they get, though.
yeah. Good. Other members of the audience or in the Zoom meeting, additional questions, feel free. Yeah, I'll raise hand, Vikas, he already.
Okay, yeah, thanks, Antonio. Dr. Baxter, just a quick one. This is very general. All this is incredibly fascinating research and just, I guess, discovery after discovery. Could you highlight some of the things that kind of really kind of knocked you back on your heels, so to speak, that you never expected this? This is the most fascinating thing I've seen, or just something that really caused you to kind of sit up and say, "Wow, this is incredible," that kind of stuff.
Yeah, that's a wonderful question. Kind of a reflection on like, oh, what, like this was crazy. Um, I think in the recent history, at the launch of the James Webb Space Telescope, we found these galaxies that were more massive than we expected, and they had shut down their star formation far earlier than our models had actually predicted. So this is telling us, okay, we got something wrong here, and we need to figure out kind of what it is. Um, and kind of to that effort, some collaborators and I, we developed, we had this model in place, but we were kind of adding some physics for accreting supermassive black holes. And we found that this model did a really good job of predicting the fraction of galaxies that have shut down star formation up until like uh, 3 billion years after the Big Bang. But the ones with JDOST was found earlier in that. So with this model, we were able to make predictions of when we would expect galaxies to start shutting down. Um, and it turns out that those galaxies that are found by JWST are likely to be having shut down by just gas being blown out by these accreting supermassive black holes, at least in the context of our models. In terms of this protocluster work, I was really kind of blown away that because this is a new field for me because I mostly just study galaxy groups and clusters in grad school. But I was kind of just taken back of like how much we did not know about these systems. So jumping into this new field and kind of learning like, oh, there's still so many like rocks that are unturned and so much so many interesting science questions to explore.
Yeah, yeah. Thank you so much, Dr. Baxter.
Thank you.
Maybe a curious question also about the models. The resolution of the models, is it at how fine a resolution do you have? Is it down to the galaxy side or size
Um,
is even smaller than that in your model?
Yeah, so typically when we talk about the resolution of the model, we think about like the size of like a stellar particle, right? So we're not resolving individual stars within these galaxies, it's usually like collections of stars. And within the TNG cluster simulation, if I remember the numbers off the top of my head, I think it's around a million solar masses is the resolution. There are some simulations that are so the issue, I guess, that we have in this field is that you have just different scales, right? So you have things that are very short distances that you can resolve those in simulation boxes that are small. But when you go to these big boxes to find these galaxy clusters, which are very huge, you just can't probe very small scales and you just can't probe very small masses. So all the work that I was doing was mostly like based down to the resolution limit of the simulation. Um, but yeah, that's just something that we're hoping, something known as emulators. We're hoping that we can use artificial intelligence to speed up our simulations and kind of be the between these different resolution scales that are right now computationally expensive to even like try to run a simulation of a, 100,000 galaxies where we have a resolution for a single stellar particle. Like right now, we can't do that, but there's folks that I know that are kind of using AI to try to bridge this gap.
Hmm. Well, that would have been the next question, so thank you. Yeah, and I imagine that increasing the resolution comes at the expense of a lot more computing
Compute.
power required. Yeah. Wow. Additional questions from anyone? Yeah, one
So
more.
speaking of computing power, where do you do your simulations? What computer do
Yeah,
you
what
use?
computer you use?
So the simulations that I use are run in Germany at Max Planck Institute of Astronomy. Um, but that's where we do our simulations. But there's folks that run them, other simulations out of Texas, some at the Flatiron Institute in New York City.
Okay, well, I want to thank Dr. Baxter again. Thank you very much. And I wish you all the success. I want to hear more, whatever you find. Maybe in a year or two, we want to hear more about what you've done. So thank you.
Yeah, I have a lot of plans, a lot of projects on the way. So I'm very excited to continue working on those and getting students involved as well.
Good, good, thank you. And I can tell the audience, this is an outstanding presentation. I actually listened to yours back last year. You put a lot more detail into this, very technically dense, if I will. Thank you. Thank you very
Yeah.
much.
No worries. Thank you.
So let me stop the recording and man, I'm gonna have to watch this recording a few times. I'm not sure I can keep up with all the things you were saying. Give me a second. Where's the recording? Come on.
Yep. And thanks, Antonio, for arranging all of these. Really appreciate it.
All the credit goes to Dr. Baxter.
And yourself. Okay, I'll sign off. I'll see you again.
Okay, you take care. See you
Okay,
tomorrow.
okay, goodbye.
Shoot.
believe I can stop it for you if you like.
Uh,
You got it, I think. Yep.
I can't, oh, there it is.